Hereby, I open this academic ceremony in which Aygül Zengin will defend the academic thesis "There's still plenty of room at the bottom. Mesoporous silica nanoncomposites for regenerative medicine applications." May I invite you to present a summary of your study and the conclusions of your thesis.
Thank you. Dear Prorector, members of Assessment Committee, supervisors, colleagues, friends, and family, thank you for joining me today. Our bodies are extraordinary machines shaped over evolution of thousands of years with remarkable healing abilities. For example, simple skin wound can heal itself in just 2 weeks. But when it comes to complex injuries, such as critical bone defects caused by trauma, infection, or diseases like cancer or osteoarthritis, our regenerative capabilities fall short. This presents a serious challenge in medicine. So, how can we help the body heal itself? One promising solution lies in the field of biomaterials. Biomaterials are specially designed to interact with biological systems. They've been used for decades for many applications, such as orthopedic joint replacements, pacemakers, or dental implants. And these innovations have already transformed many lives. Biomaterials also play an important role in tissue engineering and regenerative medicine. For instance, hydrogels. They are cross-linked polymeric networks which contains high content water, and they mimic extracellular matrix of tissues. And their tunable biochemical and biological properties create the ideal environment for cell growth and tissue repair. But, however, conventional hydrogels often lack of sufficient mechanical properties and bioactivity required for regenerative complex tissue regeneration. And microparticles are another exciting class of biomaterials. They have been used as versatile carriers for different types of cargoes, such as drugs, bioactive molecules, or cells. But they also often face challenges, such as limited drug loading capacity or insufficient control over the drug release. But biomaterials, despite these advancements in the biomaterials field, we still have room to innovate these biomaterials in a better way and improve their properties. So that's where nanotechnology comes in. By integrating nanoparticles, we can transform these biomaterials into sophisticated multifunctional platforms. In my thesis, I focus on mesoporous silica nanoparticles, or MSNs, because of their exceptional properties. First, they are biocompatible, and they have recently received FDA approval for human clinical trials. They have high surface area and stable structure. And it's easy to functionalize their surface with different types of chemical groups. And finally, their porous structures allow us to load different types of cargoes inside these pores and release it in a controlled manner. And these features make MSNs ideal candidates for enhancing the performance of biomaterials. In my thesis, I explored 2 innovative ways to use MSNs to enhance biomaterials properties. From chapter 3 to 6, I explored the use of MSNs as chemical cross-linkers to create these nanocomposite hydrogels. My aim was to investigate diverse interactions at the nanoparticle polymer interface to enhance the mechanical properties of these hydrogels while introducing new functions such as stimuli-responsive behavior or control degradation. And in chapter 7, I adopted a different strategy and used MSNs as nanocoatings to engineer microparticle surface for controlled nutrition delivery. And these concepts enabled us to use different kinds of mesoporous silicon composites for various applications, including self-healing injectables, inks for 3D printers, or nutrition delivery vehicles. Now I will focus on each of these possibilities and show how MSNs contribute to advancements of these biomaterials. In chapter 3 and chapter 5, I work on designing new type of injectable self-healing nanocomposite hydrogels, where MSNs act as chemical cross-linkers. So this type of hydrogel is quite interesting because they can mimic the natural self-healing ability of tissues, and in the meantime, they can adapt to fill irregular shapes at injury sites through minimal invasive procedures. So in chapter 3, I develop nanocomposite hydrogels by cross-linking thiol-functionalized MSNs with thiol-functionalized PEG through thiol disulfide exchange reactions. This approach stands out because, unlike the common use of MSNs as filler components, where they simply remain passive and encapsulated within the hydrogel, our MSNs actively contribute to the hydrogel network formation by forming disulfide bonds with PEG backbone. And when we look at this rheology data, we can clearly see the impact. When MSNs are dynamic covalent cross-linkers, they can improve the mechanical properties significantly. But on the other hand, when they have these hydroxyl groups on their surface, they cannot interact with the PEG backbone, and they function as fillers, so their mechanical contribution is limited. And what is exciting is these improvements in the mechanical properties didn't disrupt the self-healing behavior of these hydrogels. They still show self-healing behavior, and also these hydrogels were redox responsive, so they were degradable in presence of glutathione, which is a reducing agent found in body. In chapter 5, we took a different approach by using MSNs as covalent cross-linkers to enhance mechanical properties of supramolecular BTA-based hydrogels. These hydrogels are particularly fascinating because they mimic the fibrous architecture of the extracellular matrix and rely on non-covalent interactions. However, with many hydrogels based on non-covalent interactions, they tend to have weak mechanical properties, which limits their practical applications. So to address this challenge, we designed a hybrid network. In the system, norbornine groups on BTA fibrils were engineered to interact with the thiol groups of MSNs through photoinitiated thiolin interactions. And these interactions form a secondary network which significantly enhance the mechanical properties of BTA hydrogels. And interestingly, although we have covalent network here, these hydrogels preserve their self-healing properties. And in chapter 4 and chapter 6, I focus on developing multifunctional photocross-linkable nanocomposite inks for 3D printing applications. Here again, by using MSNs as chemical cross-linkers within the photocross-linkable networks, we aim to create bioinks with higher mechanical properties, also introduce additional functionalities like degradability or small molecule delivery. In chapter 4, I developed nanocomposite bioinks specifically tailored for extrusion-based 3D printers. In the system, thiol-functionalized MSNs form robust, stable hydrogel network with norbornine-functionalized PEG polymers through UV-initiated thiolin interactions. Different from other chapters, here I modified MSN surface with MMP degradable peptides, which allow cells to remodel their environment by secreting MMP enzymes and degrade the hydrogel network. Our degradation studies further confirm that these hydrogels can degrade over 24 days in presence of MMP9 enzyme. And our bioink formulation, which included MG63 cells, solidified rapidly upon UV exposure and formed these filament structures with good mechanical integrity. And importantly, in vitro studies confirmed that MG63 cells remain viable within the printed constructs up to 7 days. In chapter 6, we shifted our focus to volumetric printing, which is a state-of-the-art technology, allows fast fabrication of millimeter-scale constructs with complex geometries in a few seconds. For this chapter, I developed nanocomposite inks by combining thiol-functionalized MSNs with norbornine-functionalized gelatin. Here, gelatin is well-established natural polymer in volumetric 3D printing. However, like many traditional single-network hydrogels, gelatin-based inks suffer from weak mechanical properties as well. By incorporating MSNs as covalent cross-linkers, we significantly increase the mechanical properties of these hydrogels. And importantly, for the first time, we successfully use nanocomposite inks to print structures by using volumetric 3D printers. And the next step was adding new functionality to this hydrogel system. So for that, I loaded glucose into the pores of MSNs and release within this hydrogel network. So idea was releasing glucose inside the hydrogel and enhancing viability of cells in environmentally challenging conditions, like during printing or post-printing. And in chapter 7, we applied the glucose release concept to a different 3D system, and this time HMSE spheroids. Spheroids are promising biological tools for bottom-up tissue engineering. However, as spheroids grow larger, their lack of vascularization limits diffusion of glucose and oxygen to inner layers. So that results in the formation of necrotic cores. And to overcome this drawback, we use MSNs coated microparticles as nutrition reservoirs to enhance the viability of spheroids. Here, I first developed a novel strategy to coat negatively charged PLJ microparticles with positively charged MSNs using electrostatic interactions. This method results in a homogeneous and stable MSN coating on PLJ surface up to 9 days. And the next step was creating hybrid biomaterial cell spheroids by integrating PLJ microparticles coated with glucose-loaded MSNs into human mesenchymal stem cells. So our viability assays demonstrated that glucose-loaded MSNs improve viability of spheroids, even in hypoxic conditions. As I conclude, I would like to highlight the key contribution of this thesis. Here, I demonstrated how MSN cross-linkers can not only significantly enhance the mechanical properties of hydrogels, but also introduce new functions. And this research provides a versatile toolbox for scientists and engineers to design multifunctional biomaterials tailored for a wide range of biomedical applications, such as inks for 3D printers, injectable self-healing materials, or nutrition delivery vehicles. As the title of my thesis suggests, there is still plenty of room to explore. MSNs have immense potential in biomaterial design, and this work is just a small step towards uncovering their full potential in advancing biomaterials and regenerative medicine. With that, I would like to thank to my supervisors, collaborators, members of NANA Group, and funding agencies for their support throughout this journey. And now I give the back to Prorector.
Thank you very much for your presentation. It's now time to start with the opposition, and the opposition will be opened by Professor Moroni. He was chair of the assessment committee. He's professor of biofabrication for medicine at Maastricht University.
Thank you, Madam Prorector. Dear candidate, first of all, let me start by congratulating you for the very interesting work and quite also a juicy book that you have provided us to assess, and extend also the congratulations to your supervisory team for what I found really quite an exciting piece of science. Now, we have 45 minutes to still assess indeed how prepared you are as a scientist, and so let me enter into the job. As a first question, I would like to focus on chapter 4, and you have shown there this interesting hybrid bioinks. There's a mixture between your mesosilica nanoparticles and hydrogel as a carrier of them, but then when I look at the morphology of the cells that you have used, they are all relatively rounded. But then, if I understand correctly, if I remember correctly, these were osteoblasts that you use, and typically osteoblasts are not rounded; they are more spread. So, how would it be impossible to improve cell spreading in future formulations? What would you do?
Dear highly esteemed opponent, thank you for your kind words and for your question. So indeed, these cells shows round shape morphology. I think it might be related to the polymer that we used. First of all, it was PEG, and PEG is known that it's an inert polymer, and that's why we added extra RGD motifs to the system to make the network more bioadhesive for the cells. But I think the way we incorporated RGD maybe wasn't the way that we should incorporate it. I mean, so in this RGD motif, we also created a network. So they also acted as cross-linkers in this network. So there was no availability to interact with the cells. I think cells didn't really see some RGD motifs. That's why they were stuck in this confined environment without adhesive properties, the adhesive peptides, and that's why they shape this, have this shape round morphology.
You think that the RGD motifs were buried inside the polymeric network?
Yes.
Would it be possible, for example, to increase the density of the RGD or the concentration of the RGD, or maybe is there anything that you could do maybe on the, not on the polymeric side, but on the nanoparticle side?
So we already use high concentration of RGD. So maybe the way we incorporated could have been different. So now this RGD has two different cysteine groups. They interact with the polymeric network. But if we had just maybe one cysteine group from one side, one end, if they incorporated to the network, maybe they could have more chance to interact with the cells as well. So now they are completely cross-linked with the network from both sides.
On both sides, yeah. And on the nanoparticle side, I mean, of course, I mean, the focus of your thesis is using mesoporous silica nanoparticles. Are there also other nanoparticles that come to your mind that could be used in a mixture with hydrogels that may also, by their chemistry, improve cell adhesion?
Thank you for your question. So currently, mostly leponides have been used to create bioinks, especially. So because they have these 2D structures and they basically create these nanoncomposite networks through the electrodic interactions. And they also show that these nanoparticles are also bioactive, so they can induce the osteogenic differentiation of stem cells. So this can be also interesting, definitely. But
very good, very good. That's actually, laponites is what I had in my mind, so I'm very happy that you come to the same conclusion. So this, if I understand correctly, are more like nanodiscs, more than spherical nanoparticles.
Sorry?
If I understand correctly from you, these are kind of more in a disc shape, still
yes,
nanometric disc shapes, and so probably they can be packed also probably a little bit more. Before I move to my next couple of questions, just out of curiosity, as just spurring now, as you know, from the discussion, would there be any way that you could also create these mesoporous silica nanoparticles in a disc shape instead of a spherical shape? I don't know myself, so yeah, it's really an open question.
I think here, when we have these particles in spherical form, we have more surface area. And also, compared to leponides, we can functionalize the surface of these molecules with different type of chemical groups because of these silanol groups on the surface.
Sweet.
So I think, and the porous structure is also important in this spherical form to release drugs. I guess it's better if we still keep the spherical form, of course, but the disc-shaped particles also, they're interesting, but they also came with limitations, right? Because they also have positive and negative charge in the same surface. So
they may actually even repulse themselves in the packing within average. Okay. Then let me go to chapter 6. And this is a very nice piece of work, also more of a proof of concept work. I guess that if you would have had a few more months, there would be so much more to do. And so let me maybe start asking you this as a more general question. In terms of more of an application, what would you do if you would be able to continue on this work for another year?
So I really wanted to continue this work 1 year, to be honest, because I was so curious to see the effect of glucose with the cells when we encapsulate it with cells. So also, first, I would definitely look for I would do more detailed in vitro studies, how it affects the viability or even differentiation of the cells. So, and the next step will be maybe adding even oxygen releasing system inside and then combine glucose releasing with oxygen releasing and see how it will be, how it will affect the cellular behavior. And of course, it would be nice to have more complex structures to print with the volumetric 3D printers.
Okay, thank you. So if I understand correctly, combining the clinically large size that you could have with the volumetric bioprinting with the nice functionalities that you can provide with the nanoparticles, specifically in terms of aiding cells to actually survive in such larger constructs. So nanoparticles, and then of course when we come to light-based fabrication technologies, this is a bit of a compromise that you have to make, right? So more nanoparticles or more opacity of the hydrogen. What's going to be then the sweet spot here in the formulation? What actually have you tested also different kind of concentrations of nanoparticles? What would be the concentration? Do you know? Do you have an idea of what concentration could be used, where then you still have a kind of transparent formulation, so that you don't have to use the light absorber?
So, unfortunately, when we add nanoparticles inside these hydrogels, we are changing the refractive index, and the concentrations that I used for mesoporous silica nanoparticles here was 2-weight% and 4-weight%. We were able to print also these formulations as well. And also what we saw when we use high MSN concentration, the printing resolution also increased. This is also well known in the literature as well.
Okay.
So that's why also in order to increase the mechanical properties, and also here nanoparticles are cross-linkers, so we cannot really go low concentration of MSNs. So it should at least start from 1% or 2% of MSNs, which means I will have this milky white hydrogels.
Yeah.
But to modulate the color, we use iodoxinol.
Yeah. Yeah.
So this is already used in when orgonate systems encapsulated in this 3D printed constructs to reduce the refraction, the
refraction index.
Refractive index. Thank you. And and then we use the highest concentration of this solution to make these hydrogel formulations more transparent. But we should still look what is the best and lowest concentration of iodoxinol to create these inks.
Yeah, I understand.
So there are many challenges there.
Yeah, yeah. I have a few other questions, but I think our time is over. So I thank you for the answers, and I give back the word to the prorector.
Thank you very much. Then the opposition will be continued by Professor Leeuwenburg, Professor of Regenerative Biomaterials at the Radboud University in Nijmegen.
Thank you very much, Madam Pro-Rector, dear candidates. First of all, I would like to congratulate you with the completion of your thesis, and I would like to also extend my congratulations to the team of supervisors. So as a biomaterial scientist, I've read your thesis, of course, with great interest, since it deals with one of my hobbies, nanoncomposites. And in doing so, I think you have covered a very broad range, exceptionally broad range of methods and materials, so that made you really, truly a biomaterial scientist, so that's worth a compliment. Of course, I didn't come all the way from Nijmegen to compliment you for 10.5 minutes, so my task now is to raise some critical questions on some aspects of your work. So I would like to start with chapter 1. Some general questions on the main aim, basically, of your thesis. Because normally when I read a thesis, I start searching for a main aim or a main hypothesis. And I found lots of interesting information, but the first chapter is rather exploratory, and I could not really find the main aim. But so here I would like to give you a second chance to explain what was your main aim at the beginning of this thesis.
Dear highly esteemed opponent, thank you for your kind words and for your question. The main of my thesis was investigated different interactions between nanoparticle and polymer interface to enhance the mechanical properties, especially for load-bearing tissues. And also with MSNs, we explored how can we add different functions into this system.
Okay, so it's basically the interactions you were interested in to add some new perspective here. That makes sense, and I think you came a long way. So, but still, to this end, you used a wide range of biomaterials. So, and I counted 5 different polymer matrices in 5 chapters. So, in a way, that's very impressive. But it also raises a question on your reasoning. Why did you switch to another polymer system for every chapter? Was there any reasoning, or got you fed up with the previous one, or every answer is fine? So.
It's because firstly, we wanted to explore different interactions. So we started the studies with PEG thiol. And then in the chapter 3, we explored thiol disulfide exchange reaction between MSN surface and PEG thiol. And then we wanted to explore thiolene interactions for that. So this means I need to have different chemical groups on the PEG. So we shifted our focus to PEG Norbornene. So this was for us logical because also PEG gives us a lot of opportunity and room to explore different molecular weights, different structures. So then we could understand how MSNs interact with these polymers. And and then, the question comes, this is working for synthetic polymer for PEG, but how it behaves with the natural polymer. And then we included alginate norbornene, for example, to this equation. And then we try to see if we change the polymer, how it's going to affect the hydrogel formation. And for volumetric printing study, so the thing is, PEG is amazing to work with, but it's quite expensive molecule. So for printing,
Holland,
it was a bit tough. So that's why our collaborators were already using gelatin for their studies. And gelatin norbornene was a good option in that sense to see how these nanoparticles react with this kind of polymers as well. So it gives us more rooms and opportunity how this will hydrogel formation will be affected by different polymers. Okay,
so each different chapter had different requirements, and that made you, or different collaborations also.
Exactly.
So for more practical reasons, you switched to another polymer system. That makes sense. But still, of course, every answer raises new questions. So let's dive a bit deeper. And for this purpose, I would like to ask one of the paranymph, any volunteer here, to read one of the propositions, because you also wrote 10 nice propositions, and I would like to ask to read proposition number 1.
Hydrogels are the superpowers of tissue repair, and MSNs are the magic dust within hydrogels, boosting their superpowers in surprising ways.
Thank you very much for this eloquent reading. So you have a clear preference, hydrogels, and you selected quite a few of them. But then I was pretty surprised that for the final chapter, where normally this would be the culmination of your work, you moved from a hydrogel to PLJ, which is a hydrophobic polymer that does not contain any water. So do you now still support this statement, or did you still got fed up with hydrogels and all that watery stuff?
In my thesis, we mainly focus on hydrogels, yes, and the idea was making hydrogels more stronger and multifunctional. But in the final chapter, we moved on microparticles. It was because to see our glucose release concept, if it's working in a different 3D system. So at that time, because of the time limitation, I couldn't continue this glucose releasing experiments within the hydrogels. But we had this opportunity, collaboration, to see this effect in different systems. So that's why we continue with microparticles in PLGA. And PLGA is, we also PLJ was actually electrostatically negatively charged in my system, so it was already, it was a different setup. There I use MSNs as nanocoatings on this surface of microparticles.
So it's a very versatile approach, but yeah, and it worked out pretty well. So yeah, well, there's lots of choice. Let's conclude on that aspect then. I would like to now go a bit more in detail on the more scientific aspects of your work in chapter 3. Because here you introduce an interesting new concept. You want to cross-link the bond, or you want to cross-link the particles to the matrix. And to that end you use the disulfide bonds, so dynamic covalent bonds. But then I was wondering, like the hydrogel you selected in this chapter is also cross-linked by the same type of bonds, also disulfide bonds. So what is then the potential added value of adding more of the same type of bonds, hoping to strengthen your material? Is that reasonable, or did you expect other effects to be in play?
So for PEG hydrogels, yes, they also self-crossing in the system. They create these hydrogels. So when we use MSNs to this system, we wanted to explore, can we increase the mechanical properties further? And then by changing the MSN concentrations, we modulated their mechanical properties up to 25-fold. So MSNs also MSNs were also interesting components in the system, because it's known that when we add nanoparticles into hydrogel networks, they show more elastic behavior as well. So we also saw the similar behavior in our hydrogels. Okay. And the next step would be for this study, of course, adding different drugs or bioactive molecules or different kind of maybe genes inside these nanoparticles and release inside the hydrogels.
So there were more reasons than introducing dynamic bonds, dynamic covalent bonds in the system, including stiffening by silica itself, etc. That makes sense. So then another question on these bonds. Like I now understand why you switched from silanol modified to thiol modified particles, but you state somewhere, I didn't write down the page, but that these control particles, silanol modified particles, are not able to form crosslinks. But I would like to argue that, because I think silanol OH bonds can also form bonds with PEG SH, as a thiol modified PEG. So do you think that these bonds do not really count, or are they weaker, or like how do these bonds, physical crosslinks, basically relate to the chemical crosslinks that you are aiming for?
I think so. These hydroxyl functionalized MSNs probably having physical cross-linking with the polymer, somehow interacting with the polymer backbone. That's why when we also added these particles inside the hydrogels, we could also increase the mechanical properties. But when they were having thiol functions, thiol groups on their surface, they increase the mechanical properties further. So they still do cross-linking or some interactions with the polymeric backbone in summary, but it's not that when they interact with the polymer with thiol disulfide exchange reactions, they increase the mechanical properties further.
So you expect that this bond strength is higher, basically, than the hydrogen bonding that you would have for the control particles?
Could you rephrase?
Well, the control particles may also cross-link by hydrogen bonding, I think, and you expect that these bonds are weaker, basically. Or
that's true.
Yeah? Okay.
I assume electronic interactions plays a role there.
That makes sense. Okay. Is there still time for some questions? Okay, then we'll continue. Regarding this control, I was a bit confused. So I tried to find out if you really set up a nicely controlled experiment where the bond strength is varied and everything else is constant. But I was trying to find the particle size of the different particles, modified and unmodified. And there I found contrasting results. The DLS says that the silanol modified particles are larger, 248 nanometers versus 152, but then the TM, the pictures, say the opposite, and they are much smaller, the TM pictures, so I know that's challenging to characterize nanoparticles, but the first simple question is, were the thiol modified particles bigger or smaller than the control particles?
I assume it doesn't really affect the size of nanoparticles, but what we see different results for DLS and TM, it's because the techniques are completely different. And in DLS, we are mostly focused on hydrodynamic radius. And
so they're bigger?
we always, that's why, observe smaller nanoparticle size with TM, because it was in dry environment. So I think size-wise, they are quite similar. I don't expect big changes on the size.
So then I agree on the technique dependence, but I'm not still satisfied with your conclusion that size was similar, because your numbers say differently, like either they're smaller or bigger, and really by several factors. So then it's a bit mean question, but can you really attribute strengthening reinforcement of your gels to differences in bond strength, dynamic bonds, covalent bonds or not? Or could it also be a size effect, that smaller or bigger sizes may strengthen more efficiently?
Definitely, size definitely is can be effective to, it can be another a parameter for these hydrogels. We didn't really check size effect. Here, I don't expect big differences in the size. That's why I think their difference in the mechanical properties contribution will be very small. But if the size difference was like 10 nanometer and 100 nanometer, I will definitely expect to see difference in mechanical properties.
So you were saying like they're close enough, so
exactly.
You can more or less, okay, yeah. But could you really prepare the same particle with different functionalizations with exactly the same size? Is that possible?
Yes, it is possible.
Changing parameters in synthesis?
Maybe using the same batch even, and then with different...
Okay, no, but that would be nice, because then you can really fully rule out that size dependence. It is time for one final, yeah, okay. Then I would like to go to chapter 5, where you chose another gel, MBTA.
Yes.
And I think the PEC SH gel that you used in chapter 3 was performing quite well. So I was wondering why switch to MBTA. And then I was a bit surprised, because the storage modulus went down a bit, and then the yield trend went down, and self-healing was a bit less. So what was then the main reason to go to MBTA while the PEC thiol modified PEC performed so well? It's a bit a repetition of my first question, but now more in detail.
So we chose MBTA because it was also different system than what we were using in our previous chapters. So supramolecular system, more ordered systems than the chaotic, more polymeric systems. So we want to see if nanoparticles can be cross-linker in these highly organized systems as well. Because there is a high chance that they could also disrupt their network formation. So these molecules also based on non-covalent interactions, so they self-assemble into this fiber-like structures. So that's why they were having these weak mechanical properties. So our aim was to enhance their mechanical properties by using MSNs as covalent cross-linkers in the system.
Okay, yeah, that worked quite well. So finally, are you still...
Can I interrupt you, because now
yeah,
it's...
for sure. Then please, I'm satisfied with the answers.
Yeah, thank you very much.
The opposition will be continued by Dr. Castillo, Associate Professor at the Technical University of Eindhoven.
Dear Madam Prorectors, thank you. Dear candidate, let me first of all congratulate you on your work. It was a pleasure to read it. I also would like to extend the congratulations to your supervisory team, and then definitely to your family and friends that I believe they played a crucial role in helping you to reach to this stage. I have a couple of questions, more reflections that I would like to discuss with you. The first one is that you highlighted the importance of these particles to basically reinforce the mechanical properties of soft hydrogels, and you have basically indicated that your targeted tissues would be bone and cartilage. Although we as material scientists, we know that the properties of these two tissues are not just because of their composition. So what else is there that actually provides these tissues their actually quite unique mechanical properties?
Dear esteemed opponent, thank you for your kind words and for your question. As far as I understand your question, you're asking the contribution of nanoparticles inside these networks. What would be?
A bit more beyond that, because we know that, for example, bone is not just mixing hydroxyapatite with collagen, right? So what actually gives bone unique properties?
So it's also known that for mesoporous silicon nanoparticles, they show bioactive properties as well. Some studies show that having nanoparticles, these MSNs, inside the hydrogel networks, they also induce osteogenic differentiation of stem cells. So with these studies, we wanted to also, although we didn't explore in this thesis, we wanted to improve the mechanical properties and give this support to these hydrogels. In the meantime, as a future study, it could be nice to see the bioactive properties of these nanoparticles as well. So
the point that I want to, or the direction that I want to go, it's more about the structure, so the importance of structure in these tissues. And I want to use this as a bridge to the manufacturing methods that you use in your thesis. So how actually 3D printing can help you to achieve structure in your materials?
So these materials can be used as bioinks, of course, and to print these 3D structures. So 3D printer technology just enabled us to create more complex in vitro models and more customized scaffolds. So eventually, we would like to use these bioinks to print this kind of customized systems and constructs.
But do you think that 3D printing can also help you to control hierarchies in these materials? So
that can be possible, yes. And currently, I can't remember, but maybe 4D printing can help us for this.
Without going to the 4D, I think the techniques that you use already help you to actually control different regions in your material, that you have more of a phase of your inorganic and then more of a phase of your organic material. And then with these, you can actually control the mechanical properties of your material by actually structuring the materials and then controlling the regions that you have. So taking these, you looked at two printing techniques. Each of them has advantages and disadvantages. So if you had the possibility to actually repeat your work and then take either extrusion or volumetric printing, which technique would you use and why?
I think each technique has its own advantages and disadvantages. So in this case, for the materials that I develop, maybe it's better to choose volumetric 3D printers. Because in chapter 4, the bioink that I developed, at the beginning there was quite aqueous, so it was showing very low viscosity, and it was very difficult to print those systems with extrusion-based printers. So I think in order to, and also we were able to just print filaments, but we couldn't go further with more complex structures. So in this case, I will choose volumetric 3D printers to create more complex structures and also still use the low viscosity inks as well.
So it seems that you definitely have a preferred technique to work in the future. But let me maybe be a bit critical on the volumetric printing side. So in the supplementary images that you show in your chapter 6, you basically present printed structures with only a few particles distributed in your construct. So how do you actually control the number of particles in your construct, since they are actually just randomly dispersed in your resin?
This is a good question. Definitely, particles distribution is sometimes can be challenging. In the systems, we basically, before printing, we vortex these solutions and make sure that everything is distributed homogeneously. But that's why also we need fast printing times. So eventually these nanoparticles, if they stay longer in the solution, they will sediment. So
did you notice that sedimentation of your particles?
During volumetric printing part, no, we didn't.
Okay, so actually they were because you print in a more gel form, they remained in place. And then,
Exactly, because
okay, so now if I just can follow up on one of the previous discussion points about the diversity of polymers that you use throughout your thesis. One aspect that was not clear to me was you looked at synthetic and natural polymers. They have again their advantages and disadvantages. You already elaborated a bit on these. But one aspect that I'm particularly curious and would like to know your opinion is about these polymers have different structures, right? So the synthetic polymers have a more linear, of course, depends, type of structure, while the natural polymers are typically more disorganized. For the applications that you have in mind, can you select one? What will be the preferred polymer based on their organization? Can this structure of the polymer actually has an advantage or not for bone or cartilage engineering?
I think in this case, as a proof of concept, we show that synthetic polymers works very well to see the effects of nanoparticles, how they contribute to mechanical properties. But they also, although here, for example, PEG is non-immunogenic polymer and widely used, but it's also bioinert. So if we choose PEG for this kind of systems, we need to add bioactive cues inside this network. So with the natural polymers, the cross-linking of MSNs were much more challenging. Also, it was more difficult to estimate what will happen because of the batch-to-batch variation sometimes can be problematic. So in this case, natural polymer definitely something that I would go, but a bit more optimization steps and see how nanoparticles really interact with this polymer as well.
Okay. So if I can now shift gears and then focus a bit more on potential cytotoxicity of these materials that you propose, or nanoparticles, you discussed well that the degradation of these particles actually can be removed by the body up on a specific threshold. But one aspect that I am particularly concerned is that focusing again on 3D printing, if there is no fast cross-linking of these particles, we know that they can also have a detrimental effect on the cell viability. And when I look at your chapter 4, where you actually use these particles within the context of printing with living cells, I am a bit skeptic about the viability that you present, because it seems to be quite low. So do you think that the speed of the reaction and then the fact that you will have some unreacted groups in your particles could be detrimental to cell viability?
MSNs are highly known as biocompatible nanoparticles. So I think there the viability is affected by the printing procedure mostly. Because these bio-ink formulations as a solution with pegnorbornine, MSNs, and HMSCs, we extruded as a solution, and then as soon as they exposed to UV light, they created these filaments. And this maybe printing process affected their viability. But I don't think MSNs affects in this case the viability of these cells.
So it's more about the shearing of the cells that actually...
Exactly.
But so if you compare then with volumetric printing, where shearing is not a problem, did you achieve the same level of cell viability in the volumetric printed constructs compared to the extruded printed constructs?
Sorry, could you repeat the question?
So you attributed the low cell viability to basically the fact that you are shearing the cells through a nozzle or a small nozzle. My question is, if you compare to the viability of the constructs that you printed with volumetric printing, there you would expect a higher cell viability.
Yes, that would be a great to have a comparison, but we didn't have cell culture with volumetric 3D printing.
So you actually didn't perform any viability test on that?
No, we didn't unfortunately reach that stage.
So what would you expect if you just printed your materials with volumetric printing?
The idea was definitely higher cell viability, and if we include also this glucose release inside these constructs, we even want to improve these viabilities even further.
Okay. Thank you. Congratulations. I'm happy with the answers. I hand over to the chair.
Thank you, Dr. Castillo. Then we come to the last opponent. That's Dr. Bernards, Associate Professor at Maastricht University.
Thank you, Pro-Rector. I also want to start with congratulating you with your thesis and your very interesting work. Also my congratulations to the supervisors. My first question is about the synthesis of your mesoporous silica nanoparticles. You make a thiol at the surface and amine at the core. So why do you need those amines in the core?
Okay. Dear esteemed opponent, thank you for your kind words and question. So in these particle systems, so our particles show core shell structures, and this is beautiful because we can functionalize the core with different chemical groups and also surface with different kind of groups, chemical groups. So we use amine functionalize in the core, amine functionalization in the core because we thought in the future this can be interesting to label these particles with fluorescent dyes, and or we can incorporate some different kind of molecules inside. So that's why we use, but we didn't really use in our study. But the first idea was using them as fluorescent labeling.
And how do you steer the process that your amines go to the core and the silanes are at the surface?
So we are basically synthesizing MSNs. So first, MSN synthesis starts with temperature-based degradation of thiols, and then we add, in this stage, we add uptest to incorporate amine groups in the core. And then after several washing steps, we are incorporating even uptest or different thiol functionalized chemicals to the surface. So it's just part of the synthesis procedure at the beginning, how we start. So adding uptest at the beginning defines if we have amines in the core, basically.
Thanks. Then I want to go to chapter 4. So you see with your alginate, there is no, with increasing concentration of the nanoparticles, you don't have improved cross-linking. So you make your hydrogels by adding weight percentages of alginate and weight percentages of the silica nanoparticles. But isn't it better to use molar ratios of functional groups of thiol and norbornene?
So yes, generally with the other type of cross-linkers, I see in the literature they are using molar ratios. But in nanoparticle case, we don't really know how much functional groups on the surface. So here we just count on full coverage with these different chemical groups on the surface. And then for us, it's more practical to use weight-based systems in this case, because in some of the hydrogel formulations, I also use these nanoparticles as freeze-dried form. So it's for us practically much more easier.
Yes, but then you encounter things like Dr. Castillo also mentioned already, if you have then residual unreacted groups that can cause toxicity.
This is something we should definitely investigate, but in our viability systems, in this viability studies show it's really hard to so it's really hard to understand based on our experiments now if this toxicity comes from the nanoparticles or other things. And so we assume that the results also show that they are viable. So, but in order to see how MSNs affect the cellular viability, maybe we should just first, at the beginning, focus on culturing MSNs with cells. And then, which also in my group, it is done, and then nanoparticles shows good biocompatibility with different kind of cells.
And you just mentioned that you have difficulties to determine the functional group content on the nanoparticles, and that's why you did this fluorescent labeling. But do you know a technique that could determine quantitative the amount of functional groups on your nanoparticles?
Maybe we try to do FTIR. FTIR can be used, and ICP-MS and NMR also can be an option to see functional groups on the surface.
Did you think about elemental analysis?
Not really. We focus on more using fluorescent labeling-based techniques, and I also try to use FTIR, but it didn't give us the results that we wanted. Yeah. So I remember I also use Almond regions, that kind of assays to see the functional groups on the surface, but it also gave not a bit weird results with the nanoparticles as well. So it was a bit difficult.
Yeah. In chapter 4, you make the hydrogels biodegradable via the MMP cleavable peptide that you attach. But I don't fully understand how you make the hydrogel biodegradable, because you still have your thiol-norbornene crosslinks and your MMP peptide is just attached. So can you explain?
So in this hydrogel network, MSNs are crosslinkers. They are covalently cross-linked the network, but they also have surface functionality with peptides. So they are cross-linkers at the same time degradation centers. So because when we incubate these hydrogels in MMP9 enzyme-containing environment, so this enzyme specifically cleaves the specific peptide unit on the MSN surface. So, and that will degrade the network. This was the idea of the study there.
Okay, but it degrades the peptide unit, and still you have the link between the thiol and the norbornene.
Yes, that's true. And also we saw this degradation was quite slow when taking almost more than 24 days. And yes, it will degrade eventually, but there will be maybe covalent interaction still stay. But since nanoparticles are the centrals for cross-linking, and then they create these degradation points, eventually this hydrogel will degrade after a longer time of incubation with these enzymes.
Okay. In chapter 5, on page 139, you use PEG as a spacer for the MBTA units, and you write that this is a hydrophobic spacer. Can you explain me why PEG is hydrophobic?
This is a polymer. This is actually a collaboration study, so I didn't synthesize these materials, but maybe there should be something wrong because PEG is a hydrophilic polymer. Yeah. Maybe it's something. Yeah, there was a mistake there, apparently.
And in chapter 6, with gelatin norbornene, you get good cross-linking. In chapter 4, with alginate norbornene, not. What's the difference in norbornene content and molecular weight between both?
So, first of all, in alginate case, norbornene functionalization was lower than the gelatin norbornene. So I think this definitely affected the cross-linking. And the second thing is, in alginate norbornene case, we also use secondary thiol cross-linkers. So thiol, and here, probably they also interacted with this polymer and they create competition between MSNs and RGD cross-linkers. Maybe they were already saturated, so then there was no room to cross-link with MSNs. So this affected probably our hydrogel formation. And yeah, I think these are the most important differences between those.
Yeah. In chapter 7, you do coating of your microparticles. Did you study the effect of pH on the coating efficiency?
No, I didn't. I performed this coating in neutral pH. And I also performed stability experiments in cell culture media. So, but I haven't checked different pH values in this environment.
Do you understand why I ask it?
So it can change this since they are based on electrous interactions. Ionic strength also can change their interactions. Yes, I assume there might be a change, but it's hard to estimate.
Yeah. Because in fact, for both, you need opposite pH to have them in their charged form. That's, yeah, a bit... Okay. In chapter 4, why do you choose 8-arm norbornene modified PG?
Aygül Zengin, the time appointed for defending your thesis has passed. The degree committee will now withdraw to discuss the quality of your thesis and your defense. I request that you and your company await the results of our deliberations and our return in this room.
The PhD defense has now ended. The degree committee will debate the candidate's performance behind closed doors. This process usually takes about 10 minutes.
Long road to the south side. 7 miles in my rearview mirror, I know what it felt like. My goal's only getting clearer, east side to the west side. No place like home, if it's questions that you've got, go the extra mile and that. On the line, I know you know that I can't read your mind. Years can't fly by now, don't waste all your time. Cause I'll go the extra mile. Long road to the south side, 7 miles in my rearview mirror, I know what it felt like. My goal's only getting clearer, east side to the west side. No place like home, if it's questions that you've got, go the extra mile and that. On the dash, got my laces tied. Long road, I don't waste no time. Break rules because fate decides. With the team and we chase the light. I make a move, fall down, shake it off. I hate to lose, bad branch, break it off. No room for negativity, praise and love. Prepare for deep part cause we're taking off. The mileage, traveling so far from home. Gathering knowledge, other connections. I put the time in to get everything I ever hoped for. It's a challenge and we all in. It's a better future that we go for. And even though these nights seem long, I know that I am never on my own. Know you've won the battle once you've grown. To the south side, 7 miles in my rearview mirror, I know what it felt like. My goal's only getting clearer, east side to the west side. No place like home, if it's questions that you've got, go the extra mile and that. Long road to the south side, 10 miles in my rearview mirror, I know what it felt like. My goal's only getting clearer, east side to the west side. No place like home, if it's questions that you've got, go the extra mile and that. What's on the line? I know you know that I can't read your mind. Years can't fly by now, don't waste all your time. Cause I'll go the extra mile.
Aygül Zengin. The degree committee here present has assessed the quality of your thesis and your defense. In view of its positive verdict and taking into account your previous qualifications, the degree committee has decided to grant you the degree of doctor. Professor Habibovic is authorized to confer upon you this academic distinction in accordance with Dutch university custom. I invite your supervisor to now take the floor.
Do you promise to work in accordance with the principles of scientific integrity at all times, to be careful and honest, transparent, independent, and responsible?
Yes, I promise.
By the authority vested in us by law and in conformity with the decision of the committee here present, I hereby confer upon you, Aygül Zengin, the degree of doctor and grant you all rights attached by custom and law. As evidence of this, I now present to you the degree certificate signed by the rector, the secretary, and the other members of the committee, and affixed with the official seal of the university.
Het woord is aan uw promotor, Dr. van der Rijt.
Dear Dr. Aygül Zengin, it is my great honor and privilege to be the first to officially address you as doctor and to congratulate you on this remarkable achievement. Today, we celebrate not just the years of dedication and hard work, but also many milestones along your journey that brought you here. You began your PhD in 2018 as one of the very first PhD candidates to join the MDR gravitational program and the second PhD to be welcomed into my lab. The project was relatively undefined at the start, and together we embarked on the challenging yet rewarding journey of shaping it. We envisaged using silica nanoparticles to enhance the properties of nanoncomposites for in situ bone regeneration, and I feel confident to say that we were right. Your research demonstrated how the mode of nanoparticle incorporation, the hydrogel backbone, and other parameters influence mechanical and self-healing properties, critical factors for successful application. You went further, showing that these composites could be engineered for 3D printing applications, a significant achievement that expands the practical relevance of your work. Your contributions have laid the foundations for much of the ongoing research in our lab, and for this, I'm deeply grateful. Beyond our group, your pioneering efforts have made us one of the few labs exploring dynamic inorganic nanoparticle incorporation into hydrogels, amplifying the impact of your work on the broader scientific community. It is with the funding of the gravitational program of NWO that we were able to explore this new topic, and I think we can only hope that such funding will be available in the future so we can keep doing this type of curiosity-driven research. Doing PhD is a journey, a transformative process filled with both triumphs and challenges. It is a path of personal and professional growth, where persistence, curiosity, and resilience shape not only the scientist, but also the individual behind the research. Of course, no journey is without its challenges. Shortly after you began, the COVID-19 pandemic struck, disrupting not only research, but also our personal lives. The lab closures of 2020 were particularly challenging, but you faced this period with resilience. I still remember how you welcomed Lumi, your cat, into your life, a companion who now graces the cover of your thesis. about beautiful illustrations. Your presentations always brought a unique touch, whether it was a comic reference to Futurama or other nice artwork. You have a way of adding a bit of fun and relatability to your work and your presentations. You are a passionate researcher. I will always remember the infectious enthusiasm you showed when experiments worked, the determination with which you tackled challenges, and the ability to pick yourself up when things didn't go as planned. Next to your enthusiasm, I would say your biggest strengths are your scientific curiosity and your collaborative nature. You have the ability to connect ideas, people, and disciplines. This combination of strengths led to several great collaborative projects and publications. For instance, you wanted to explore if our nanoncomposites could be optimized for 3D printing applications. What initially seemed like a relatively simple endeavor turned out to be a slightly more complex challenge. That was successful due to trial and error. Thanks to your perseverance, but also the support of our colleagues Carlos and Filipa, this project reached a successful conclusion. You also started a collaboration with Shazad, just by having a chat in the lab. And you immediately started to do some initial proof of concept experiments together. And I remember when you approached Matt and myself with the idea, very enthusiastic, and we liked it very much, but we worried that you wouldn't be able to complete it because you were so close to the end of your PhD contract. But then you managed to convince us with your enthusiasm, and this led to a nice publication that we recently published. Over the years, we had many conversations, science and other topics. I fondly recall our conversations during conferences, which ranged from academic insights to discussions about politics, but also lighter topics like travel and food, especially cheese. Admittedly, we are both a bit stubborn, a quality that led to some spirited debates. But as I see it, this type of stubbornness is a strength in academia. It drives innovation and keeps us striving for better answers. What I admire about you is your kindness and inclusivity. You have a way of making everyone in a group feel welcome, regardless of their background or interests. This quality is rare and invaluable, and it has made our lab a better place. Thank you for that. The path to completing your thesis was not easy, especially during a time where life presented you with additional challenges. But you persevered, showing dedication to deliver the thesis we celebrate today. You managed to publish 4 excellent articles and contributed to a book chapter. These contributions have culminated in a beautiful written thesis we have before us today, a result you can and should be incredibly proud of. Before I conclude, I want to express my gratitude to Pamela, who also supervised you. You gave us the freedom to explore this topic, but at the same time gave insightful and useful feedback and guidance that helped shape the research. I also want to thank our collaborators, Carlos Mota, Filipa Taxera, Matt Baker, Niloufar Birgani, Maria Foua, Shazad Hafiz, Ricardo Levato, and Mark Valland, as well as the Assessment and Promotion Committee for their contributions and presence here today. Thank you, Lorenzo, for creating an environment where people can work together and learn from each other. Thank you, Sander, for our nice scientific discussions over the years and inviting us to visit your institute. I hope we can find new opportunities to work together in the future. And thank you, Miguel. It's been great getting to know you and your science over the past years in the MDR. And thank you, Katrien, for being here today as a fellow chemist from Maastricht University. I hope we can keep strengthening this discipline in Maastricht in the future together. Dear Aygül, congratulations once again on this extraordinary milestone. This day is not just a celebration of your success, but also a moment to acknowledge the support of your family and friends, both here and online, who have been with you every step of the way. I'm confident that you have a bright future ahead of you in Groningen, filled with exciting opportunities and achievements, and I wish you all the best, both in your career and in your personal life. Enjoy this well-deserved celebration. You've earned it.
Dear Dr. Zengin, also on behalf of Maastricht University, I congratulate you with the degree you have acquired. I also congratulate your family, friends, colleagues present here or probably also online, who supported you one way or the other during your PhD journey. I'd like to congratulate your supervisors with this nice PhD defense and I'd like to thank the members of the degree committee for their contribution to this PhD defense, and especially our guests from outside, Professor Leeuwenburg and Dr. Castillo. Thank you for coming to Maastricht. Your contribution is very much appreciated by the university. Yeah, I think for you it's now time to relax and enjoy the degree you have obtained. I hope you enjoyed also the defense. From looking here, I think, well, that was okay. You feel comfortable. And of course, you always think, oh, I should have said this or I should have said that. That would have been better. But that happens to everybody, I can assure you. So now it's time to enjoy the fact that you obtained this degree, and I wish you a very pleasant day. With this, I close this academic ceremony.